Hi everybody, in this video we're going to be discussing this idea of symmetry and graphing, okay? And symmetry with respect to the fact that what we're trying to do here is sketch images or sketch pictures of graphs that maybe represent variable relationships. But these graphs tend to be probably more difficult than a standard graph, which we probably recognize from algebra, which would be like a line or a parabola. Maybe we have something that's rather complex, and so therefore, knowing maybe a little bit about its symmetry before we isolate a variable or make a table of values and plot points would actually give us some insight into how the graph might behave. And so here's the thing about it. I'm going to start by talking a little bit about the different types of symmetry in the XY coordinate plane, the rectangular coordinate plane, and the Cartesian coordinate plane. Okay, starting with x-axis symmetry. Okay, so it is what it says it is, and when we talk about symmetry, what we're really doing is really kind of bring up the fact that something can be like a mirror image. So when we say x-axis symmetry, you can imagine this x-axis right here as being what we call the line of symmetry. But an example of something that would exhibit x-axis symmetry, what if we considered maybe like a sideways parabola, okay? But the fact of the matter is this: if we knew a graph before we isolated variables or plotted points, if we knew a graph was going to exhibit x-axis symmetry, and say we knew half of the graph, the convenience here is that we would be able to sketch in the other half of the graph without actually having to do a whole lot of work, okay? So this would be an example of something that has x-axis symmetry. Something that would have y-axis symmetry, of course, but we don't even have to, be centered at the origin. But what if we had another parabola that opened up? Okay, it would have y-axis symmetry. And then we have origin symmetry, which basically, we say, when we talk about origin symmetry, what we're really saying is that a graph would be symmetrical about this line y equals 1x. Or to be very technical, we say y equals 1x plus 0, where this line has a y-intercept of 0, that's our plus 0 there, and a slope of 1. Okay, so, but a graph that maybe would exhibit symmetry about the origin would be something necessarily like maybe a hyperbola that would behave like this, okay? So let's talk about y symmetry and what symmetry necessarily means. Now, when I said mirror image, what we're really, kind of putting out there is this, that you could fold necessarily half the graph over this line of symmetry and on to the other half of the part of the graph. But when we're discussing like x-axis, y-axis, and origin symmetry, what we're going to do is go back and play on this thought that when we talk about the x-axis, we're really saying that all of the y values of all the points, so the y values of all the points on the x-axis happen to be the value 0, and all of the x values on the y-axis happen to be 0. And when we talk about origin symmetry, we can kind of play off these two. But that's important because what I can tell you is this. Let's go ahead and try and illustrate this. What if we had a graph that exhibited symmetry about, say, the x-axis? Well, what we could say about this is, given some point, any point on this graph here, we could say we could trace a straight line distance back to this line of symmetry. And what would have to be true is, if we headed that same distance on the other side of this axis of symmetry, we would have to land at its mirror image point. But the unique thing here is this. This is some given x value right here, okay? And given this x value, what we can say is this x value actually happens to proceed to this positive y value. And this x value also happens to proceed to this negative y value. Now, the same can be said about any point over here, say, on this graph that exhibits y-axis symmetry, okay? But if we were to find this distance back to this line of symmetry, which happens to be the y-axis, which happens to be this entire line that has x values equal to 0, we say if we were to do this, then it would be the same distance on either side, but there would have to exist a mirror image, which is unique in the sense that given this negative x value here, okay, this negative x value, it goes to this positive y value, this height value. But if I were to give you, say, even the positive x value, it would also proceed to this positive y value. Okay, so we've got a mirror image reflection about the y-axis. And then last but not least, what if I were to say, give you this point over here? We could even say, given some positive x and negative y. The fact of the matter is this. If we were to draw this straight line distance back this way to this line of symmetry, and I know it's kind of hard to fathom with my drawing here, but what you would realize is we actually end up with this negative x and positive y value. So you're going to notice some things here, and let's go ahead and start talking about this over here, but you'll notice first things first, with origin symmetry, we can observe that given some point okay, if you were to flip the sign of both of the x and the y value of that point, you would land at this other symmetrical point on the other side of the line of symmetry in which both the signs have been flipped. And then we can go over here and talk about these respectively as well. But with x-axis symmetry, you'll notice that both x and positive y and both x and negative y are on here, but that the y sign is flipped. So for x-axis symmetry, you'll see that both the positive y and the negative y apply. And then over here, likewise, with y-axis symmetry, you'll notice that x kind of changes its value. So basically, let's explore this a little bit here. But, you know, we had a really interesting graph in the last example, and that graph was of this equation y equals x squared minus 2. And I'm bringing this up because, you know, it's a good habit to start talking about these things, but we say we've already got y isolated. Let's go ahead and make a table of values. Well, you know, might be familiar with these values. Plugging in these x values, though, we say negative 2 plugged in here squared is 4, 4 minus 2 is 2, negative 1, comma, negative 1, 0, comma, negative 2, and then negative 1, and then we're back up to 2. But we had this graph before, and the thing I want to point out here is this. Recalling this graph, or if you're just tuning into this video, we can graph this right now, but once we've got this table of values, it really gives us a lot of insight into this graph. And we could check for intercepts as well, which is something we did in the last video. But in this video, we're discussing symmetry, and this graph happened to exhibit what we would call y-axis symmetry. And the y-axis symmetry exists because of the fact that this graph is a mirror image on the left of what it is on the right. Okay, so here's what I really want you to notice is this. Basically, you know, let's pick on a couple of points here. How about we pick on this one here and this one here with this y-axis symmetry. But we say this is the point negative 2 comma 2, and this is the point 2 comma negative 2. But essentially what I'm saying here is this. It wouldn't matter with y-axis symmetry if you had plugged in a negative 2 or positive 2, and we can just prove that just by looking over here. If you would have plugged in a negative 2 or positive 2 for your x value, these two x values right here, in both instances you would have yielded a positive 2 for a y value. It's indiscriminate. It doesn't care. You're still going to wind up back at that positive y value. And what that does is now give us sort of some insight in how to check for symmetry. Okay, so we're gonna list some checks for symmetry here, but we say symmetry checks. Okay, maybe we want to check a graph for symmetry. Oops. Before we graph it, in order to kind of gain a better perspective of what this graph might look like. Okay, so we say the three types of symmetry, starting with x-axis symmetry. We say x-axis symmetry. What we can say is this. In order to check for x-axis symmetry, we'll say plug in a negative y. So x-axis symmetry will plug in a negative y value for all original y values of the equation. Okay? We say if this results in the original equation, then, okay, so then the graph will exhibit or show, you know, it'll exhibit x-axis symmetry, okay? So if it was me, you know, and I was in class and I wanted to learn more about symmetry, this is something that I'd write down here. And this is all, we'll say this is bullet point number 1, but of course, bullet point number 2 is going to be y-axis symmetry. And what I can tell you is this y-axis symmetry, we can go ahead and note this. We'll just plug in negative x for all x and ditto. Essentially what we're going to say here is this. If you were to plug in a negative x for all original x values into the equation, and when I say ditto, here's what I mean. I'm going to mention this. It's the same thing as what you had kind of written up here. If this results in the original equation, then the graph will exhibit x-axis symmetry. Essentially what we're saying is, say for example y-axis symmetry, which this graph exhibited, we're saying that if you were to put in this negative x value or this positive x value, you're essentially going to result in the same exact thing as what you started with. Or in other words, this y value that yields is going to be the same regardless. And the same thing goes for this x-axis symmetry. We say to check for x-axis symmetry, what we'll do is we'll plug in a negative y wherever we saw y in the equation. And if we result in the same equation, then we'll have, you know, a confirmation that this has symmetry about the x-axis. And so looking at this, we say, okay, what if we did plug in a positive y here, or say a negative y here? In each case, you'd end up with the same x regardless, or you'd end up with, algebraically, the same equation. Okay, and then the third check for symmetry, we say origin symmetry. Respect to the origin, okay? So origin symmetry, or about the line, the line y equals x, okay? And so we're going to plug in negative x for all x, and, okay, negative y for all y. And then we say, okay, and ditto. If we end up with the same equation we started with, what we're going to have is this idea that we'll have symmetry about the origin. Okay, so the best way to do this is, you know, I can talk all I want about this, but the best way to do it, I believe, in my own, what you want to call maybe professional opinion, is the best way to do this is just kind of explore it by doing it.